All right, so let's look at another example. So at a gathering of n randomly chosen people, what is the probability that at least two will have the same birthday? All right, now we first compute the probability that nobody has the same birthday, and then we'll use the complement rule to find the probability of interest. So in computing the probability that nobody has the same birthday, note the following. The number of ways to choose different birthdays for n people is given by 365 permute n. Right? Another way to think about this is we've got n people whose birthdays we need to select, and they all need to be different. So the first person, the first birthday, there are 365 ways to choose that birthday. Then for the second person, because it needs to be different, there are 364 ways to choose that birthday. And so on down to the nth person, all right? And so there would be 365 minus n plus 1 ways, right? That can be calculated or expressed mathematically very succinctly by 365 permute n. In addition, the total number of ways to choose birthdays for n people without any constraints. So in that situation, we're allowing birthdays to be different, to be the same, and so forth. So the total number of ways to choose birthdays for n people is given by 365 raised to the nth power. Because for each person, there are 365 ways to choose their birthday, and there are n people, and so by the fundamental rule of counting, the total number of ways of doing that would be 365 times 365 times so forth, out to the last person, which is 365 ways to choose their birthday. So 365 multiplied together n times, and so that is 365 raised to the nth power. And so, and let me just go back up here and say that, note that we're assuming here that the people are chosen randomly. And so what that means is that all possible birthday situations are equally likely. So the number of, so that the probability that no birthdays are the same is going to be given by this number divided by this number. All right, so the probability of no birthdays the same, if the people are chosen at random, is 365 permute n divided by 365 raised to the nth power. So that is the probability that no birthdays are the same. Now the complement of that event is that there's at least two people that have the same birthday. Okay, so at least one birthday is the same. And we can get that probability from this probability by subtracting this one from 1. All right, this is an application of the complement rule. And so the probability that at least one birthday is the same is going to be 1 minus the probability that no birthdays are the same. And so 1 minus 365 permute n over 365 raised to the nth power. Now, one question of interest. How many people must be present in order for the probability of at least one birthday to be the same to be at least 0.5? All right? Now, we can take this formula and start plugging in values for n, the number of people that have been selected, until we find an n for which this probability is at least 0.5. And if you plug in 22, you'll find that the probability that there's at least one birthday the same is 0.4757. So 22 people is not quite enough. But with 23 people, the probability that at least one birthday is the same is just a little bit over 0.5. So you would have to have at least 23 people at the gathering for there to be at least a 50% chance that at least two people have the same birthday. Okay, now this slide shows the calculations done on the TI-84 using that formula, and I plugged in 22 for R in this case, and then 23 here. And so you can see we get the same values for these probabilities, 0.4757 and 0.5073. Okay, let's look at some more examples. So suppose that a softball team has 12 players on its roster. In how many ways can players be assigned to the 10 field positions for the start of the game? All right, so we need a roster, all right, for the 10 field positions. In how many ways can we do that? Well, we've got 12 players to choose from. Let's just suppose that we're not really interested in, who's best at playing a particular position. What is the total number of ways that we could assign 10 people to the field positions when we've got 12 people to choose from? Well, that's going to be 12 permute 10, all right? It's an arrangement. We can think of the positions, listing out the positions. That would be an arrangement of positions, all right? Because each position on the field is is specific. It's different. First base is different than second base, which is different than third base, and so forth. All right. So these different positions on the field correspond to different positions in the list, in the arrangement. All right. And so the number of ways that we can do this is surprisingly big: 239,500,800. So there are a lot of different lineups, a lot of different ways of assigning 10 people to the 10 positions on a softball field when you've got 12 people to choose from. All right, and this just shows the calculation on the TI-84. All right. Okay, now we're going to look at the third counting technique called counting combinations. So suppose that we have a collection of n distinct objects. What we're interested in is counting the number of subsets, which are also called combinations, of R objects taken from the set of n objects. Now, in this situation, when we talk about a subset or a combination, the order or the arrangement of those objects is not important. All right? It does not matter the order that they're selected, or the way that they're listed, or the way that they are arranged. All right? So this is necessarily going to be a lot smaller than the number of permutations. So the number of subsets, or the number of combinations, we've got two different ways of denoting this. Now, this notation here is perhaps more prevalent. It's more commonly used. All right? I'm going to use both of these pieces of notation, but this one is definitely the one that's more commonly used. And let me just point out that this is not a fraction. Right? There's no division bar here. This is just notation specific to counting combinations. All right? And this notation is read n choose R. Okay, so how many ways can we choose R objects from a set of n objects? Now, another way to denote this, and this is a way that is consistent with, for example, the TI-84 calculator, all right, is this notation here. So this is very similar to how we denoted permutations, but here we're counting or denoting combinations. And so this would be read n choose R again, n choose R. Now the formula for counting combinations is given by this expression here. And that is equal to n factorial divided by the product of R factorial and n minus R quantity factorial. Okay, so let's derive this formula. So the number of such combinations, which again are unordered subsets of R objects taken from a set of n objects, is commonly denoted by this notation here, as we've discussed, as well as that notation there. Now, to find a formula for this number, let's consider the following procedure for counting the number of permutations of R objects taken from the set of n objects. Now, we're going to be ultimately here deriving a formula for the number of combinations, but what we're going to do first is think about calculating the number of permutations of R objects taken from a set of n objects. Now recall that the number of permutations of R objects taken from a set of N objects is given by, or denoted by, that notation there. Okay, so we're going to think of constructing a permutation. All right, we're thinking about this as a two-step process. And so what we're going to be doing is ultimately using the fundamental rule of counting as well. So let's think about constructing a permutation of R objects taken from a set of N objects. And so the first step in this process would be to select a subset, a combination, an unordered subset of size R from the set of N objects. Okay? So we're selecting an unordered subset or a combination of R objects from the set of N objects. Now, the number of ways that we can do that, we've not determined yet, but we do have notation for that number, and that notation is N choose R. Now, once we've selected that unordered subset, in order to get a permutation, all right, we need to permute or arrange the R objects. And the number of ways that we can do that is R factorial, right? Because we've got R objects that have been selected. All right, so once we select our R objects, an unordered subset of R objects, then step 2 is to arrange those. All right, there are N choose R ways to do this first step. There are R factorial ways to do the second step. And so then by the fundamental rule of counting, the total number of ways that we can construct a permutation of R objects taken from the set of N objects is N choose R times R factorial. And that gives us this number of permutations that we are, at the present time, trying to determine. All right? So let me just point out we have an equation here, and there's only one thing that's at this point unknown. We know the formula for this quantity, and we know what this quantity is, but we don't know this one. And so to get the unknown, all we have to do is divide through by R factorial. And so that's what we're going to do. So solving for N choose R, it follows that the number of combinations of R objects taken from the set of N objects is given by this expression here. Okay? And so that's the formula that we had before that we showed, and this is how you derive that. Okay, going back again to the probability submenu of the math menu on the TI-84, we see here that the third option, the third submenu option, N choose R, that's going to give us the number of combinations of R objects from the set of N objects. Okay, let's look at some examples. All right, so this first example asks us, in how many ways, how many committees of 4 people can be formed from a group of 12 people? Now, there's no other constraint besides selecting a group of 4 people. There's nothing that would say that the order that they're selected is important. There's nothing that says that the people have different positions on the committee. It's just a group of 4 people. And so this is an unordered subset of the 12 people that we have to select from. And so what we're going to count here is the number of combinations, right? And so the number of committees of 4 people that can be formed from a group of 12 people is 12 choose 4. And it turns out that that's equal to 495. All right, and if we use the TI-84 calculator to calculate that, all right, we get that same value. Okay, so this is an interesting example. Consider the Powerball multi-state lottery. All right, so maybe you've played Powerball occasionally. How many different Powerball tickets are there? And then once we calculate that, we want to answer the question, what is the probability of winning the Powerball jackpot with one ticket? And then what is the probability of winning the Powerball jackpot if we buy two tickets? All right, so let's take a look. So to count the number of different Powerball tickets, consider the process of constructing a ticket. Now, it's always a good idea when we do this to go to the Powerball website and check to make sure that they haven't changed it. If they do, we'll take that into account. All right. But the current way that that Powerball works is that you've essentially got, you can think of a bucket that contains 69 ping pong balls. The balls are numbered 1 through 69. And they randomly select 5 balls from that first bucket. The second step is to select what's called the Powerball from a different bucket. That is in the Powerball bucket, they've got 26 ping pong balls, numbered 1 through 26. And so once you've selected the first 5 balls from the first bucket, and then selected the Powerball from the second bucket, then you have a particular ticket. Right? You have the winning ticket. And so the total number of ways that we can select balls in this fashion, according to these 2 steps, gives us the total number of possible Powerball tickets. Now, this is a 2-step process. In each of these 2 steps, we're counting combinations, but then we put it all together by using the fundamental rule of counting, because there are 2 steps here. Regardless of how many ways step 1 ends up, step 2 can be done in this way. This one does. So how many different ways can we select 5 balls from the bucket that contains 69 balls? Well, that's 69 choose 5. Again, it doesn't matter the order of that the balls are selected out of that first bucket. All right, the order does not matter, and so that's why we're counting combinations here. And 69 choose 5 is a rather large number, 11,238,513. And then for each one of those ways, there are 26 choose 1 or 26 ways to choose the Powerball from bucket 2. And so by the fundamental rule of counting, the total number of different Powerball tickets is equal to the product of these 2 numbers, 69 choose 5 times 26 choose 1, and that turns out to be 292,201,338. All right? So if you've got 1 ticket, so if you buy 1 ticket, what is the probability that you win? Well, there's only one way to win. If their random process for selecting those balls matches with the numbers that you've got on your ticket. Right? And because they're doing this randomly, they're doing it in such a way that every possible ticket has the same chance of being selected, the probability that you win with 1 ticket is equal to the number of ways that your ticket could win, which is 1, divided by the total number of possible Powerball tickets, which is 292,201,338. And so that ratio, right, this is the probability of your winning with 1 Powerball ticket. Now, if you happen to have or buy 2 Powerball tickets, then there are 2 ways that you can win, right, corresponding to the 2 tickets that you have. So if they select either of your 2 tickets, then you win. Okay, so the probability of winning with 2 Powerball tickets is 2 over that large number. Okay, so in both cases, very unlikely that you're going to win. Now, what is the probability of not winning with a single ticket? Well, this can be calculated in several ways. For example, it can be calculated directly by noting that at a given drawing, there is only 1 winning ticket. Now, understand that multiple people may have that ticket, but in terms of the number of winning tickets, there's only 1 winning ticket. And so that means the number of losing tickets is 1 less than the number of total tickets. So 292,201,337. All right? And since each ticket has the same probability of being selected by virtue of the way that they are selecting the balls out of the buckets, the method of determining probabilities based on equally likely events gives us that the probability of not winning the jackpot with 1 ticket is 292,201,337 over 292,201,338. So it's virtually assured that you're not going to win. Now, another way to calculate this, perhaps an even easier way, is to use, once again, our friend, the complement rule. All right? Because the event not winning is the complement of the event winning, by the complement rule, the probability that you do not win with one ticket is equal to 1 minus the probability that you do win with one ticket. All right? And so we just subtract this probability from 1, and we get the answer. Now, thinking back to when we first started talking about how to quantify chance, we talked about probabilities, but we also talked about odds. And so let's just think about what are the odds of winning with a single Powerball ticket. Now remember that the odds of an event are given by the odds of that event divided by the odds of the complement of the event. Sorry, let me restate that. I stated that incorrectly. The odds of an event are given by the probability of the event divided by the probability that the event does not occur. So the odds of winning with one ticket for Powerball is equal to the probability of winning with one ticket divided by the probability of not winning. All right? And so all we have to do is plug in these probabilities that we've already calculated. All right? And we see that the odds of winning are 1 over 292,201,337. Now, the reason I throw this in here as part of this example, and this is easier to show you and explain if we're actually in class, but if you go to the Powerball website, and if you search around until you find the page that gives you what they call the odds of winning, they're actually not giving you the odds of winning. That page gives you the probability of winning. But they've mislabeled that page as the odds. All right, and I just use this to point out that the odds of winning Powerball are slightly different than the probability of winning that they give on the page. And what they give on the page for the probability of winning is exactly what we've got right here. Okay? Okay, so this just shows calculations for this example done on the TI-84. So calculating the 69 choose 5. And let me just point out, this is going to be much, much easier to use a calculator to do this than trying to do it by hand. Now, you certainly don't need to get a TI-84 calculator to do these calculations. If a calculator does at least 2 sample statistics, it will almost assuredly have buttons that will allow you to calculate combinations and permutations as well as factorials. Okay, so just search around on your calculator, make sure that you know where this functionality is and know how to use it. Okay, so I think I'm going to stop this video at this point. They don't want us to make these too long, and so we'll pick up with some additional examples in the next video.